So welcome you all to today's lecture. So what we were discussing was Bayes and Minimax estimation. So we had some discussion on Bayes estimation, the conditions under which Bayes estimator is admissible, the condition under which a Bayes estimator can be minimax, and then we were studying the minimaxity. And under minimaxity, basically we try to find a decision rule which minimizes the maximum loss, or in other words, I try to find out estimator delta star for which supremum risk is minimum. What we saw is there is a close relationship between Minimax estimator and Bayes estimators, in the sense that if you have a Bayes estimator which has a constant risk, such a Bayes estimator we saw that is minimax. So that is a result which we saw last time. And then we said that, okay, if you have to find a minimax estimator, what you do is you try to find out a family of priors, find out a Bayes estimators corresponding to them, and try to now play around with the parameters involved in the prior distribution so that the risk of the corresponding Bayes estimator becomes a constant for some choices of parameters of the prior distribution. If that happens, I readily have the minimax estimator available with us, and we saw an example of a binomial distribution. I also noted the point that unlike the usual risk, unlike in the case of usual risk comparison, when I talk about Bayes estimation or the minimax estimation, the constant factor which depends on theta and is associated with the loss function, that plays an important role. So for example, if I have a loss function of this type, let me do this, c theta times w of a minus theta in the location case. When I am comparing the risk in the usual manner, that means in the frequentist approach, this constant doesn't make any difference because I try to compare the risk for every fixed value of theta, and normally this c theta is non-negative. So this would be common to the risk of all the estimators. But when we talk about the Bayes estimator, we talk about the average loss in certain sense, and average is over the theta. So this c theta would play when I take the averages over all thetas. Similarly, in the minimaxity, this c theta will play a role, because when I take the supremum, this supremum c theta would play the role when I take the supremum. So what we were then saying is, okay, so if Bayes estimator has a constant risk, it is minimax. But in certain situations, what may happen is a constant, there will be an estimator which has a constant risk, but it is not Bayes, actually it is a limit of the Bayes. Now even if that happens, I would say that the corresponding estimator is minimax, and that is the result I am talking about now. So theta not. So let pi m be a sequence of priors delta pi m is the Bayes rule corresponding to pi m, corresponding to pi m with Bayes risk let us say Rm. So Rm is the Bayes risk of the Bayes rule corresponding to the prior pi m. And suppose delta naught is a constant risk estimator. So here when I am talking about constant risk, it is a risk in the usual sense, that is the frequentist sense. So that means R theta delta naught is C for every theta belonging to theta naught, and this C is constant. So let us say R theta delta naught is R naught. R naught is a constant. And what I assume is This delta naught is a limit of a base in the sense that the base risk Rm go to R naught, this constant risk of delta naught. Of course, this constant risk would also be same as the base risk of delta naught because it is constant. So when you take the average over theta, you get R naught only. So in other sense, what it's saying is you have an estimator with a constant risk such that the sequence of base risk converges to this constant risk R naught, which is also the base risk of delta naught. If that happens, then delta naught is minimax. The proof is simple. I have to just approximate R naught through Rm. So fix epsilon greater than 0. I fix epsilon anything arbitrary greater than 0. Then there exists m naught, which already depends on epsilon, such that Rm would always be between R naught minus epsilon to R naught plus epsilon. Now what I have to show is delta naught is minimax. So what I try to do is I take any other estimated delta star and I would show that the supremum risk of delta star is always bigger than or equal to supremum risk of delta naught. So let delta star be any other estimator. I have to compare the supremum risk of delta star with supremum risk of this delta naught. So then supremum over theta belonging to theta of R delta star theta. Now note that supremum is always bigger than or equal to average. So this would always be greater than or equal to R delta star of pi m for any pi m, because you take average, you can take average with respect to any prior. So supremum is always greater than or equal to average with respect to any prior pi m. So supremum is always greater than or equal to average. But I know that corresponding to prior pi m, delta pi m is the base. So that means the base risk of delta star would always be bigger than or equal to base risk of delta pi m under the prior pi m. So this would always be greater than or equal to R delta pi m pi m. All right, for every m greater than or equal to 1, and which is basically nothing but Rm. R delta pi m is the base risk of the base rule, which is nothing but Rm. But Rm is always greater than R naught minus epsilon for all m greater than or equal to m naught. So this is always greater than or equal to R naught minus epsilon for every m greater than or equal to m naught. But R naught is the constant risk of delta naught. So that means supremum risk of delta naught is also R naught because delta naught has a constant risk. So this is same as supremum over theta belonging to theta of R delta naught or R theta delta naught minus epsilon. All right, because R naught is the constant risk of delta naught. So R naught would be also same as supremum. So what do you get? You get supremum over theta belonging to theta of R delta star. I'm interchanging. Sometimes I'm writing down the risk as R delta star theta, sometimes R theta delta star. So I think it's clear from the context. So this is always greater than or equal to supremum over theta belonging to theta of R theta delta naught minus epsilon. So whatever epsilon may be, this is always greater than or equal to epsilon. Now epsilon is arbitrary. So I can make arbitrarily small, epsilon to be arbitrarily small. Or in other words, I can take limit epsilon going to 0. So I get from here supremum over theta belonging to theta R theta delta star is always greater than or equal to supremum over theta belonging to theta of R theta delta naught. So what you have proved? You took any arbitrary estimated delta star, you showed that its supremum risk is always bigger than or equal to supremum bisque of delta naught. And that proves that delta naught is minimax. So note that this result is quite useful in many situations. For example, under the squared error loss function, you know that whatever Bayes estimator you get, if that is unbiased, it cannot be Bayes. So the unbiased estimator which you get, that may not be Bayes, but it may be a limit of the Bayes. So proving the admissibility of such an estimator may become easier if you use this result. For example, I am talking about normal theta 1 under the squared error loss function. Then x bar is a UMVE. I would like to see whether x bar is minimax or not. I know that x bar has a constant risk. Now if it was Bayes, then by the result which we did last time, it would have been minimax. But I know that under the square error loss function, any unbiased estimator cannot be Bayes. So x bar is not Bayes. But the question is x bar now limit of Bayes in the following sense? That is what we have to see. So let us try to see that, and we'll prove that x bar is in fact minimax. Okay. So let us do this example. So let x1, x2, xn be IID, normal theta sigma naught square, where sigma naught square is known. For estimating theta under the square error loss, which is L theta A, is nothing but A minus theta whole square theta and A belonging to R, so that delta naught x, which is x bar, is minimax. Note that we have already shown that delta naught is admissible, and the result used was that it is limit of Bayes in certain sense, so it would be admissible. Now here I have to show that it is limit of Bayes in certain sense, in the sense that limit of Bayes risk goes to the constant risk of delta naught, and then we are done. So that is what I have to show. So proof, I know that R theta delta naught is nothing but sigma square by n, because it is a variance of x bar for every theta. So it is a constant risk estimator. So if I can show that certain Bayes risk converges to sigma naught square by n, then x bar would be minimax. So if you recall, we had considered a priors while proving the admissibility of x bar. We had proved that let us consider a sequence of priors to be pi m, which is normal 0 m. M greater than or equal to 1. Now for such a sequence of priors, I had seen that posterior distribution, in fact if you recall, it was nothing but normal, again because it is a posterior distribution that we have derived. And what was the mean? Mean was the weighted mean of the prior and x bar. So x bar, that means n by sigma naught square x bar, plus its mean is 0, so that will not get contribute anything, and the weight is n by sigma naught square plus 1 by m. 1 by m is coming from here, and it is 1 upon sigma naught square by, so which is a variance of x bar. So this and what is the variance? Variance is 1 upon n by sigma naught square plus 1 by m. So I have just to see what is the, now for the square error loss function, Bayes estimator is the posterior mean. So delta pi mx is nothing but nx bar, n by sigma naught square divided by n by sigma naught square plus 1 by m into x bar. This is a Bayes estimator corresponding to the prior pi m. So what I have to show is, if I can show that the basis of these Bayes estimators converge to sigma naught square by n as m goes to infinity, I am done. And this, the hint of the prior we got from our earlier lectures. So let us look at Rm, which is nothing but R delta pi m. Pi m, this is what I have to find. Okay, so let us first try to find out its usual risk, R theta delta pi m, which is nothing but expected value of n by sigma naught square divided by n by sigma naught square plus 1 by m x bar minus theta whole square. What is this? This is a mean square error, which is same as variance plus bias square. Variance of this would be this square. So n by sigma naught square whole square divided by n by sigma naught square plus 1 by m whole square into variance of x bar, which is nothing but sigma naught square by n. So this one would go away and they will be left with only this quantity, n by sigma naught square, plus bias square. Bias would be this into theta minus 1. So theta square would go away and this minus 1, right? So this minus 1 is how much? N by sigma naught square or n by sigma naught square gets cancelled. So 1 by m whole square divided by, right, bias whole square. So this minus 1, so 1 by m, yeah, n by sigma naught square plus 1 by m whole square theta square. And where does this goes to? As m goes to infinity, this goes to 0. So this is by n by sigma naught square, n by sigma naught whole square. So this is 1 by, so this is sigma naught square by n. So this goes to sigma naught square by n. As m goes to infinity, this goes to 0, because this goes to a fixed quantity and this goes to 0. So this goes to as m goes to infinity. And this is same as the constant risk estimator, the risk of the estimator delta, constant risk of delta naught. So R theta delta naught, or which is same as R naught. So this implies that delta naught is minimax. All right. So this simple application, you can apply this result in variety of situations. Now let me do a result, the following result. Let us see this. x1, x2, xn are IID, normal theta, normal mu sigma square, where theta is equal to mu sigma, which belongs to r cross 0 to infinity. Let me call this as theta, is unknown. I consider my loss function to be L theta A, which is nothing but A minus mu whole square. xn can be anything in the real line. Now in this case, note that if I look at x bar, my x bar has a risk sigma square by n. Now in this case, sigma is unknown, so it is not constant. So the question is, can I say my x bar is also minimax even when sigma is unknown? So that, so in fact with this case we'll see that all estimators are minimax. You consider any estimator which is minimax, and it is minimax with supremum risk as infinite, with supremum over theta belonging to theta, r theta delta as infinite for every delta belonging to d. So it says that you consider any estimated delta, the maximum risk can be infinite. So for all the estimators, maximum risk is infinite. So all estimators are equally good, or all estimators are equally bad in terms of the minimaxity criteria. So I can say that all estimators are minimax, but the maximum risk for all the estimators is infinite. The proof is almost straightforward. It follows from the case of known sigma square. So now first I fix sigma square. Now if my sigma square is fixed, then I know that my x bar is minimax. X bar is minimax, what does that mean? Its maximum risk is smallest. So that means maximum risk of any other estimator would be bigger than or equal to maximum risk of this. So that means supremum over mu. Now the maximum would be only with respect to mu. So supremum over mu belonging to r theta, let me put it, delta would always be greater than or equal to the maximum risk of x bar, because sigma square is fixed, so it is always greater than or equal to sigma square by n. For every mu belonging to r, and whatever sigma may be, whatever sigma you fix, for any estimator, supremum over mu belonging to r. So what I do is, now I take supremum over sigma also. So this implies that supremum over theta belonging to capital theta of r theta delta would always be bigger than or equal to, I can make sigma arbitrarily large, infinite. So which is basically saying that this is always same as infinite. So all estimators have a maximum risk as infinite, so all estimators are minimax. Now let us try to see what is the problem over here. The problem is because this, if sigma square is completely unknown, this may just explode, and that may make the risk of all the estimators to be infinite. Now the question arises is, suppose I have a prior information that sigma square cannot explode, or in other words, I have a prior information that sigma square is always bounded above by a constant c. Then can I say that still all estimators are minimax? And the answer is no, because if sigma square I know that it cannot explode beyond certain limit, or in other words it is bounded above by c, then I may be able to get a minimax estimator. But before that, let me do this result. So suppose I have a parameter space theta naught, which is contained in theta. Delta naught is minimax under the parameter space theta naught. Note that minimaxity also depends on the parameter space, because you will be talking about supremum over different sets. So supremum over different sets, different estimators may have a minimum of supremum risk on different sets. So that is why the minimaxity also depends on the parameter which you are considering, parameter space which you are considering. So delta naught is minimax under theta naught. We also have that supremum risk of delta naught under theta naught and theta is same. So supremum over theta belonging to theta naught of r theta delta naught is same as supremum over theta belonging to theta of r theta delta. So for example, this would always be the case if delta naught has a constant risk. Then whether you take supremum over theta naught and theta. So this condition will be satisfied by any constant risk estimator, which is minimax. Now if that happens, then delta naught would also be minimax on the larger parametric space. So let me write down. Is also minimax under theta. That means the bigger parametric space. How do you prove? The proof is straightforward. So let delta star be any other estimator. Then what I try to show is supremum of risk of delta star over theta is bigger than or equal to supremum risk of delta naught over theta. And that is straightforward. What happens? I consider supremum over theta belonging to theta of r theta delta star. Now you know that supremum over a bigger set is bigger. So if I am taking a supremum over a bigger set, so if I have two sets, theta naught and theta naught, theta is bigger, then if I take the supremum over capital theta, that will be bigger than the supremum over the smaller set, which is capital theta naught. So here, since theta is bigger, supremum over bigger set would always be greater than or equal to supremum over theta belonging to theta naught. For infimum, it is other way. Infimum over a bigger set is smaller, right? Okay. But I know that my delta naught is minimax under theta naught. So that means the supremum risk of delta star would always be bigger than or equal to supremum risk of delta naught under theta naught. That is by the minimaxity of delta naught under theta naught. But supremum over theta belonging to theta naught of all theta delta naught is same as supremum over theta belonging to theta of r theta delta, right? By the condition which is given to you. So what does that mean? I took any arbitrary estimated delta star and I showed that its supremum risk is always greater than or equal to supremum risk of delta naught, and that proves that delta naught is minimax. And that proves the result. Now what I can do is I can look at a simple application of this result.